Yes. Uh, Thank you very much for this opportunity to explain our climate design overview presentation. And I hope this presentation will be the good basic knowledge for the people who would try to build their own space elevator climber, especially for double spec. So from now, I would like to explain about the climate design overview. And this material and presentation was made by Ikeuchi Ryo, a regular member of JSEA, and he's an engineer. And in this, especially for aerospace engineering field, is his major. So let's start. And I'll share the presentation material. This, yes, grammar design overview. And now I will explain some background on climate design. Okay, and this is space elevator climate design on space elevator challenge in Japan. We have been conducting the Space Elevator Challenge in Japan from 2009 annually, and perhaps more than 150 climber have been built in Japan, include the German team, excellent Space Elevator climber. And now the maximum average speed of space elevator climber up to 100 kilometer vertically, or in these days, some climbers would achieve up to 200 kilometer for ascending speed. And next is some another example of climbers. And this is so I afraid that the band-wise of each participant, if small, it would be difficult to watch. But this is the climber test scene in Japan. So in next November, we will conduct this kind of competition. But in these days, the high price of helium gas, then we can't use the helium balloon. Then we use the cliff to deploy the tether for climbers ascend and descent scene. Okay, next. This is another scene. This is a typical climber ascending scene. Okay. And from now, it's not so fun, but I'd like to explain about the space elevator matter. If someone start to building climber, then this kind of information would be necessary to start. So in Japanese history, climber community would take several years to achieve this knowledge point. But in these days, this kind of theory or strategy is exist, and start to climb a building would be much more easier. Yes, and let's start. When designing a climber, the key point to consider are the following three design elements, just like with robot and automated machines. There are three: climber, electrical system, and control. And climber means the mechanism. And the next, so that first, I'd like to explain the climber design, mechanical design. Okay. And at first, we have to think about the tower design. When designing the climber, the first thing that needs to be designed is the power design. When designing from lightweight values as shown on the left, we first set the target values. then carry out a preliminary climber design, calculate the power, determine the engine speed, and then design the climber in this order. Uh, the target setting is the amount of control required for transportation, the combined weight of the climber and the payload. Then set the low angle speed, the acceleration. Next, as a tentative design, we will tentatively determine the diameter of a wheel. To calculate the power, we use this formula to perform the power law delivery room. When it comes to determining the prime mover, we set it based on the power supplied voltage, and mass. And once that decided, we then proceed with the design, include climate design, principal cost, prime mover mechanism, transmission efficiency, etc. So we design these, and if the numbers doesn't match, we go back to setting the target values or back to setting the limit machine, and we go through the cycle to refine the design. And when designing from the limiting movement capacity, the next, and I continue power design. As I said earlier, it is same. You set the target location and then you set the limiting movement. After that, a preliminary climate design is made and expected usage is announced. And then the climate design is carried out last. Power design, this is an example. This is an example of designing from calculated power values. If the transport control weight is 15 kilogram, the low speed is 2 meter per second. The acceleration is 1 meter per square, 1 meter second square. And the diameter of the wheel is set to 15 millimeter. Then the steady state automatic response will be obtained, like on this PC, value PC. I set the symbol PC. Then the automatic acceleration is calculated in a similar way to PA, parameter PA. So the necessary power can be obtained through calculation. So from there, we select the motor, and in this case, we decide on the motor with a low power of 1 kilowatt, a low precision rotation speed of 8,400 revolution per minute, and the low precision torque of 1.2 Newton meter. At this time, the weight of the motor was determined to be 1.33 kilogram. The motor driver weighed 1.05 kilogram. So the total is 2.41 kilogram. So we can roughly determine how many kilograms are left in relation to the climber's weight for the frame, power transmission mechanism, brakes, and so on, and how much more can be used for these things. And then before the motor starts to rotate, we need to determine the gear ratio. But to get the torque we need for the torque speed, we need to set the gear ratio. This is the calculation formula. The gear cost is 3.38 is obtained, but to have some torque margin, we set the safety factor at 2. So in this case, the gear ratio is set to 6. So now that the gear table has been decided, we are checking the rotation speed of the same wheel here too, to see if we are achieving a rotation speed required for the targeted top speed. Whereas for the revolution per minute, it stopped at the low probability original RPM and gear ratio. the relationship equation. So we will calculate it here. I continue power design. First of all, we'll talk about electric motors, but basically, climbers are powered by electric motors. So I'll introduce you to electric motors. There are three types of motors structures, brush motors, sensorless brushless motors, and brushless motors with sensors. Each has its advantages and disadvantages, but in the case of brush motor, it's very easy to control and it has a simple structure in that it will rotate on its own. If you apply voltage, and it's also very inexpensive, so the good things about it is that because it uses brushes, brush maintenance is required. Then sparks are generated from the brushes, so we have decided that we must take measures to reduce the noise from these sparks, especially for computers or another thing. Oh, I'm sorry. Sensorless brushless motors are easy to obtain in high output types, and they are basically maintenance free. But the downside is that when you start them up, you need to rotate the motor a little. So if the motor doesn't rotate due to the load on the climber, you can often find yourself in a situation where you can't keep the motor rotating. So this is the decision. And again, since most of them are for hobby use, if has been decided that there are not many that provide detailed specifications. Next, regarding brushless motors with sensors, the advantage is that it is possible to provide guidance at the time of issuance. This sensor detects the position of the motor's rotation, and the motor drive can determine which layer the current should flow through. This means that, like a sensorless brushless motor, it is maintenance-free. However, the downside is that it is difficult to obtain high-output models. Out of these three, it is best to choose a brush motor for production, brushless motor for production. Next, continue power design. However, depending on the mechanism, sensorless brushless motor can also be used. Next, regarding the low rating of the motor, this is also the definition of the term. But low rating is a number that determines the output of the motor, and by using it within the specified range, it is a number that will prevent damage to the motor. However, as I said earlier, there are almost no low value will indicated for hobby brushless motors. You can't know the actual brushless motor characteristic. I think they do have a low output, and there are motors that have an output written on them, such as 1 kilowatt. But most of them don't say much about what the conditions are. So basically, I don't think they can be trusted. So regarding low probability, there is the concept of continuous low rating and time low rating. Continuous low rating means that even if you continue to use it continuously, the garages will basically not break. And continuous low rating is what determines the maximum value that can be obtained. On the other hand, the time is less accurate, and if it is within a specified time, the maximum value that can be output is specified. So if it is 10 seconds or 1 minute, for example, then this much output can be output. However, if you continue to output more than that amount of time, it will break down. When it comes to choosing a power source, we recommend industrial motors whose specifications are detailed. However, as I have been saying, it is rare for hobby motor to be listed as having low reliability. So if you do use one, it would be good to be able to test it in advance to make sure it is suitable for use. If we can do a continuous load test, I think we'll be able to make a rough judgment. And the next is braking method. Next, to eliminate the climber moment is important, but just as important are the brakes. I'll give you a brief explanation about the different types of stopping. First of all, there are two types of brakes, mechanical and electric. Mechanical brake, like disc brakes, use friction to maintain their position. When something moves, most of their kinetic energy is converted into thermal energy. As for mechanical brakes, there are things like bicycle disc brake and electromagnetic brakes, and they are very easy to obtain. So I think we'll basically be using these. And as for the electric brakes, the kinetic energy of the vehicle at the time is used to generate electricity and convert it into electrical energy. There are various types of brakes, such as regenerative brakes that return electrical energy to the battery. Regenerative brakes that convert the generated electrical energy into heat using resistors, and current brakes that generate an electrical current to obtain power. Next, continue braking method. Next, there are positive brakes and negative brakes things. Positive brakes are the type that apply force when braking, like the brakes on car or bicycle. On the other hand, negative brakes are like elevator brakes. This actually means that the brake is always applied, and when you want to release the brake, you input a force. So climbers are basically the same as elevators, so they need to be equipped with negative brakes. This is of course a given, but if the power goes out, the brakes will not longer work and it will be completely unsafe. So it is important that the brakes can still be applied even if the power goes out. So as for installation, an example of something that is very easy is a radius electromagnetic brake, which apply the brake when the power is turned off. So I think that selecting the appropriate one and installing it is the easiest way to install it on a climber. As for positive brakes, I think it would be good idea to use a combination of mechanical and electrical brakes. Since it is a climber, the best thing would be to use a revised brake system that returns the power to the battery. But technically, this is quite difficult. So I think it would be good to have a mechanical positive brake as something that combines a disc brake and the electromagnetic brake. Next. So, as a way to improve the braking mechanism, as I mentioned when explaining the motor, I mentioned a little about the problem of the sensorless motor not being able to start climbing if the load is too high when it is rising. But by combining this with an emergency brake, I think we can come up with a solution to this. So as I was just introducing it, if the brake is released too early, the motor will be overloaded and it will not be able to start. But there is also the method of releasing the brake and pushing it manually when starting the climb. But if the climber is heavy, this can be quite difficult. So this is just a temporary solution. So, so in response of that, by combining the parking brake and one-way clutch, you can create a mechanism that allows free rotation in the upward direction, and you can raise the vehicle while keeping the parking brake applied. So I think this is one solution. The parking brake, this is a battery brake, etc. And it is a rotary brake. And these another things called a neutral brake, which apply the brake to the tether and uses the response of the servo, the brake servo. So when this is a force that tried to make the climb fall down, the brake are applied more strongly. So when the climber tries to rise, the brake has the feature that the brake can be released with a light force. So combining these kinds of things is one countermeasure. So when these brake mechanisms are used, one thing is that the manual assistant that was previously used as a temporary measure becomes unnecessary. And when timing is critical, the brake releasing time can be easily, so that an advantage. The advantage of this is that the energy required to release the brake can be made smaller. And I'd like to explain about the drive wheel of climber. So in usual, climber would use the urethane roller or gum roller to climb up the tether, climb up against the tether with the friction. Next, regarding the immobility of the climber, when the climber ascends, the driving force needs to transmitted to the device so that the climber can ascend reliably. And one item that needs to be taken into consideration is the coefficient of friction. So in order for the climber to perform the stabilization, this formula needs to be satisfied. The coefficient of the friction and free pressure need to be greater than the driving force. If the driving force is greater, slippage will occur. So in terms of driving force, it's the aircraft's gravity flow rate and the acceleration that was set during the design and the gravitational acceleration. Combining all of these, we can calculate the driving force required, for electricity. So with regard to the wheel pressure force, it can be controlled to a certain extent through design, but as for the friction coefficient, it is a characteristic of the materials. So it is necessary to have some data from experiments at actual speeds. So if you don't know the coefficient of friction between the materials of your climber, the material of the wheels, and the tether, then as shown in the picture below, you can use the killing material and the handrail. I'm sorry. I'm sorry. And the wheels. And you can use the killing material and the handrail and weights and pull them with a bar, and then you can conduct an experimental to measure the coefficient of friction. Electrical system design. As for the transmission configuration, in the case of automatically controlled climber, basically it's become like this kind of configuration. For the effort ticket, we basically use batteries, a drive battery and control battery. So the microcontroller controls the whole things, and the motor motor drive the motor, which generate unwanted course. So the climber's movement are measured by sensors, and that inform is feedback to a microcomputer. Power system. As for power supplies, as I explained earlier, there are two types: drive power supply and control power supplies. As for drive power supplies, they are basically high voltage, high current systems such as 12 volt, 24 volt, and 48 volt, which are used to supply power to motor driver. The most powerful power supply is a voltage meter, such as 3.5 volt or 5 volt, which is used to supply power to the machine control system and the speed meter system. So basically, there are two power supplies, one for driving and one for controlling, and that's the basic configuration. So when you accelerate, a voltage effect occurs, and the control computer will drop, or if the battery drops, even if the drive battery drops as long. As the control battery is still alive, it is possible to understand what the situation is. So we have separate them into two, and these are the type of batteries. In terms of types of batteries that are easy to obtain, I think there are about three options available right now. The first one is nickel metal hydride battery. The cell voltage is 1.2 volt, which is basically safe, but it is not very energy efficient, and the weight per cell is also heavy. So basically, the majority to terms use lithium polymer batteries with a cell voltage of 3.7 voltage. It is extremely energy efficient. The advantage is that it can also draw a large current from the electrode. However, if handled improperly, there is a risk of fire, so it is important to handle it safely. However, up until now, there have been almost no times that have caused this battery to burst into flame while in the process. It looks like this. So basically, you should be careful when charging or storage it. And then there is the lithium ferrite battery. This is also a lithium battery similar to the lithium polymer, and as a cell battery at 3.2 voltage, the energy efficiency is lower than lithium polymer, but in terms of safety, this lithium ferrite is better than lithium polymer. Battery selection. So in terms of battery selection, if the power design is done properly, when battery selection is relatively easy. As for the battery, you have options such as mechanism to provide one with a certain voltage or whether you need one with a watt-hour rating. But in this case, we'll basically be thinking about the capacity. For example, if the output during ascent is 1 kilowatt and the ascent time is 20 seconds, then the energy required during ascent is uh, uh, 1000 by 20 divided by 3600, which means that you need a battery of at least 5.56 watt. So let's say you bring a 48 voltage 1000 watt battery. The battery capacity is going to be 48 watt, so we can confirm that it will meet our requirements. Also, from the capacity, we can estimate how many times various actions are possible, various ascent and descent. So when we conduct an experiment, we can figure out how many more attempts we can make. And if we keep a proper record of how many times we have erased the action from the time it is fully charged, we can get a rough idea of how many times we can do it. So we have done the rough design calculation here, but things like losses during voltage conversion, consumption during operation, etc. are not included in the calculations. So basically, we look at the battery capacity and selection it based on a safety factor of 2. And so basically, I think it is reliable. And the motion control. Now let's talk about motor control. So it is an input command to the motor driver, and it's a motor driver for hobbyists. This is common to both brush motor and brushless motors, but basically they have a signal called a PWM, pulse wave modulation input. This is a basic common pulse wide modulation, and the period is set at 20 milliseconds. So if you set the signal time to 1.5 millisecond, the motor will stop. So if you set the signal to 2.0 millisecond, the motor will rotate at its maximum speed, so it's a format signal. On the other hand, industrial motor drivers have their own input specifications. So for example, with 6 inputs, some control the rotation speed in proportion to the input voltage. In the range of 0 to 5 volt, some control the rotation speed in proportion to the input voltage. Some use pulse input, and some control the rotation speed in proportion to the frequency of the input pulse, and some use serial input such as RS422 or 485. And other communication in a specific format. So there are input command methods that are suitable for each motor driver. And this is all of my presentation now. So, but this basic design explanation materials continue, and this is half of whole explanation. But today, I think that it's too much for the people who see the this kind of material. Then I am now stop now. But a few days later, this material would be possible on internet, and perhaps everybody would be possible to use and consider the contents of this material. That's all my presentation. Thank you for your attention.